Our motivation for this project is the presumption that distance perception is compressed in virtual environments compared to real life. This compression has been discussed in quite an amount of papers, and the reasons for the phenomenon is still to a large degree unknown. We found research suggesting that an immersive environment could possibly increase a user's sense of presence, which in result can have a positive influence on distance estimation. Consequently, we chose to investigate how we could influence immersion and presence. One of the ways of increasing one's presence is incorporating embodiment, the sensation of being and feeling like the subject of an experiment. Based on this, we chose to investigate how embodiment influenced distance estimation in our initial experiment. The participants would be placed in a 3D replica of a real-life room, with a basketball placed on the ground in a distance from them. They would then be asked to assess that distance. The embodiment used for the test only included head and hand tracking. The lower body movement was animated based on position change. The results showed significantly higher scores in self-assessed presence with embodiment, as well as higher precision and significantly higher accuracy of distance estimation compared to no embodiment. To dive deeper into the topic of depth perception, we investigated how humans' depth perception is affected by a variety of depth cues, classified into binocular and monocular cues. Since no single depth cue is always available or always reliable, only combining multiple cues can provide correct distance estimation. As the results from the initial test suggested that embodiment could in fact affect depth perception in virtual reality, it was decided to further investigate the occurrence, with a focus on the aforementioned depth cues. For our next test, we therefore decided to group the objects into two scenarios: grounded, where the objects would be placed on the floor of the room, and floating, where the objects would be placed floating in the air, which would require the participants to perceive different depth cues in order to estimate the distances. Due to the participants' feedback from the initial experiment, we chose to disable the animation of the lower body and instead have it motionlessly follow the headset position. For the final test, participants would be placed in the same 3D replica of the same real room, this time with spinning cubes spawning on the ground and in the air, in different distances to the participant. As in the first test, they would then be asked to assess the distance. The results from the final experiment showed that changes made after the initial experiment decreased the sense of presence in most cases, which could be due to the sense of the embodiment lowering itself, possibly due to the body being less responsive and more static. In relation to distance estimation, it can be noticed that there could be a correlation between presence and distance perception. Presence was significantly higher for the with embodiment condition in the initial experiment, while the distance estimation also showed a higher precision and significantly higher accuracy. Opposingly, for the final experiment, the presence showed no significant difference, correspondingly to the accuracy and precision of distance estimation, which also did not show any significant difference between the conditions. Moreover, the analysis of the results only between grounding and floating scenarios, without regards to the conditions, showed a significant difference in favor of the grounded objects. Thank you for your attention.